No.
Shorted resistance right here. It ignores these two, so those aren't part of it.
Okay, so there's 200.
So it's just 3 and 4. So they're
Huh? Huh?
current splits proportionally.
That is the what the current separation principle. It does separate based on it's an inverse relationship between the resistances. So more current is going to go to a lower resistance than a higher one. No. Okay. For those of you on the live stream, I would pause this video and do this assignment before I walk through this, because you're going to learn more if you try it yourself first. I'm going to assume you paused it, so I'm just going to keep going. All right. So basically, with this problem, we have all of these resistances. All of them are equal to 100, and we want to know if we can create an equivalent resistance, equivalent circuit between A and B. Okay. So now that we have that, as you're aware, we're going to have to solve this system twice. Once with an open circuit, once with a closed circuit. Just by shorting that, it does change the circuit entirely. So there's no easy shortcut to getting around this problem. But that said, that stuff we did over here, that was like, and now we're going to try to figure out what the voltage source is for a Thevenin equivalent. We don't have to do that because we already know. Okay, so let's save ourselves the effort. I like to prove things and then never go back. All right. Okay, here's the problem. Now, what we're going to have to do is we're going to have to build a series of equivalent circuits to try to break this down. You could use node voltage analysis or mesh current analysis to figure this one out. But I don't really want to solve a matrix in the middle of class and try to, go through that.
I'm just here for the chat.
No, I don't think I could do that again in my life. Dang it. Okay. All right. I don't even know where I was at. Let's just solve this thing. All right, so the first equivalent circuit that we're going to go ahead and build. We've got these two in series, we've got these two in series. I'm going to combine both of them, okay? When we combine in series, we lose a node. So we're going to lose node 3, we're going to lose node 5. And what we'll end up with here is shoot doot 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 shoot doot 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 shoot doot 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 doot.
I could combine those two.
Beep 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 beep. Okay. All right. Yeah, I did. I grounded it at 4. I always try to put the ground on the other end of the.
Switchboard by around.
No.
Yeah, that's. I think 5. The last number should always be the 0 voltage.
Well, fine. You can draw your circuits that way. Okay. Good for you. All right. So here, this is REQ. We'll call this REQ1. We'll call this REQ2. This is R1, and this is R2. Okay. And here we know REQ1 is equal to R5 plus R6, which is equal to 100 plus 100, which is equal to 200 ohms. Okay? And then we also know that REQ2 is equal to R3 plus R4, which is equal to 100 plus 100, which is equal to 200 ohms. Sweet. All right, now we have this circuit. Now we do have this one in parallel. We'll go ahead and combine that one quickly. So here we have the next circuit that we have is shoop, 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 shoop. This is REQ1. This will be REQ3. This is REQ2. Now we did lose a loop when we combined in parallel. which is fine. And this is 4, this is 2, this is 1. We'll go ahead and ground that. Okay. So here, REQ3, 1 over REQ3 is equal to 1 over R1 plus 1 over R2, which is equal to 1 over 100 plus 1 over 100, which is equal to 2 over 100, or 1 over 50, which means REQ3 is equal to 50 ohms. Okay? So that's nice. We have a 50 in there now. Okay? Next step, we have 2 resistors in series. So the next one we have is shoop, 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 where this is REQ1 and this is REQ4. Here, REQ4 is equal to REQ3 plus REQ2, which is equal to 200 plus 50, which is equal to 250 ohms. Okay? Now we have these two in parallel. Shoo-boop. So we reduce it down to a single resistor, REQ5. And here, REQ5, 1 over REQ5, is equal to, yep, I'm off camera. Thank you. Ah, dang latency. We're just gonna get that skew angle here. So it looks like I'm bigger over here, but then like I go down and I'm like, look, I'm shorter.
Yeah,
Wow.
you turn up your latency.
You're not gonna get stream sniped.
Yeah.
Wait, did you just say turn off my low latency?
Yeah. No, you're high latency.
Yeah, that was what I meant.
Oh, turn off the, oh yeah, enable the low latency, got it. I mean, it could, but, oh well. So we've got 1 over REQ5 is equal to 1 over REQ1 plus 1 over REQ4, which is equal to 1 over 200 plus 1 over 250. I am not doing that in my head. Oh, look, a calculator. Nice. I don't know whose this is.
11.11. 100. Oh yeah, 111. And then it becomes 11.
I'm gonna make sure that that's right.
1, 1, 1, 1, 1. The decimal after the
There's a decimal after the first 3 ones. There's just a lot more words.
I don't know how to shut this off. Friggin' HP. Dang it. All right, so anyways, REQ5 is equal to 111.11 ohms. Okay. Any questions on how we got here? Personally, I walked all the way from my house. All right, so what we can do in this situation is we can figure out, we know what the current source is, it's 0.1 amps. We know that there's only one resistor in this entire circuit, so we can figure out what the voltage is at 1, between 1 and 4, okay? So VREQ5 is equal to IREQ5 times REQ5, okay? We know this, we do not know the voltage, so we just plug in numbers. VREQ5 is equal to 0.1 times 111.5. Where did I get the 0.5 from? No clue. So VREQ5 is equal to 11.111 volts. So now we know that there is 11.111 volts between node 1 and node 4. If you really want to keep track of your node voltage table, okay, thank you. Can I see all the way to the end of the board? Almost. I do. It'd be fun. I'm doing it right now.
Oh, there he is.
It's laggy.
I can go back and watch me do it again. Nice.
No, you just watch you just go.
Oh,
like
now
this.
he's doing it. Yeah.
Yeah. We need to be done. We need to be done. I don't want to spend any more time with you either. So if I were to keep track of a node voltage table, I got my node, I got my voltage, I got 5 nodes, and then I've got A and B. A and B, A is at 1, B is at 2. So I'm just going to denote that up there. I know voltage at 1 because I just figured that out. Voltage at 4 is 0. Voltage at 1 has to be 11.111 volts, okay? Sweet. So then the next step is we have to take one step back in this circuit and figure out how much current is going through this portion of the loop, okay? So, we take our voltage in, we put our resistance there. That song fell apart quickly.
All about
Do the hokey pokey and you.
what the numbers about.
That's what it's all about. Sounds like we're some kind of a government force. Yeah! Resistance! All right, let's be done with that too. We just really need to be done with today's class. All right, so we'll take VREQ4 is equal to IREQ4 times REQ4. Here, we know the voltage, we know the resistance, we do not know the current. We're solving for the current, okay? Yeah. 100, nope, that's 11. 11.111 is equal to IREQ4 times REQ4 is, wow, why is this smudged? Who did that? That was my hair. Oh well. Times 250. Okay. So quick maths.
I kind of figured out where we were at.
Zero.
What are we solving for?
We're trying to figure out the current in REQ4.
11 divided by 250. 0.0.
At 0.044.
You got what?
0.044.
Yes, I'm fine.
So IREQ4 is equal to 0.044. Repeating?
Yeah.
Okay, I'll just add a couple more 4s. All right, so now we know how much current is going through this piece of the loop. Okay? Now we know how much current is going through this piece of the loop. So now that we know this current, we can solve for the voltage between 1 and 2. Once we solve for the voltage between 1 and 2, we're done. With this one, we have to do it again. But we're done with this piece. So now we want to know VREQ3, which is equal to IREQ3 times REQ3. We already have this value, we already have this value. This is 50. This one is 0.04444. So what is VREQ3?
2.22.
Okay, so there is 2.222 volts between A and B. I'm going to go ahead and just plug that in here. This ends up becoming, what, 8.999? No, it's like 8.888.
Yeah, 8.88.
Yep, volts. And I'm just going to leave that there. I don't need to know any of the rest of this. This is 11.111. This is 8.888. And the difference between these two is 2.222, okay? That's all we need to know for this circuit. The next step is to short that. Okay? No, we don't need to find any of the rest of it. I mean, you can if you want, but I only care about the voltage between A and B.
It's that squiggly.
Draw like some lines.
Okay, bro, I don't know how good of an artist you think I am, but I ain't drawing no Star Wars shit.
You just have to do a little line around that.
Pew, pew, pew. Have you ever heard like a whole herd of blue jays all calling to each other? It totally sounds like ATSD's shooting. It's amazing. All right, now I did erase all of that because all of that work was for that last half of the problem. We're on a new half, different world, okay? So I'm gonna take this and create an equivalent circuit. In this equivalent circuit, I'm going to combine these two. What I'm also going to do is I'm going to completely ignore these.
You erase VOC. The 2.22.
Do you remember? your-
Thank you. Thank you. I appreciate that. Okay. So I'm going to combine these two. And the second piece is I'm going to completely ignore R1 and R2. Why am I ignoring R1 and R2?
They're shorted.
Because they're shorted. Why does that mean I can ignore them?
Because there's a path of less resistance, so it's not going to go through a resistance path.
Path of least resistance. There's zero resistance here. These have a positive resistance. There's no voltage between A and B in a shorted circuit, which means there's no voltage across R1 and R2. It is as if they are open circuits because there's no current flowing through them, okay? So we can just simply ignore them. We'll combine these two and we'll combine these two. And the resulting system that we get looks like this, okay? We'll call this REQ1, we'll call this REQ2, and this is still IS. We still have node 1, we still have node 4. We collapsed 5 and 3 when we combined these two, and we collapsed 1 and 2 since we shorted it. Did I lose anyone? Do I need to say that again?
You lost
Yeah, and Gerardo. But assuming they're going to be on the live stream. I assume they will. They're pretty good students. Huh?
You only have one viewer right now.
Well, they're all in class. I would hope they're not sitting in Joel's class like, this is good. What is he even doing with that? What? I don't even know what that is.
It's currently like 7 and 8 p.m. for the Russians. Where are they at?
Yeah, they should be
Yeah,
dinner.
it's horrible. My Russian viewership has dropped 100%.
I don't want to watch the channel either.
Borscht. I'm getting my borscht. It's time to log into my favorite YouTube channel. It's this idiot in America who teaches children. All right, come on, let's be done, please. All right, REQ1. We're combining these in series, so REQ1 becomes R5 plus R6 because that's a series equation, which is 100 plus 100. This is 200 ohms. REQ2. Again, we're combining these two in series. This is R3 plus R4. We combine them in series. It's 100 plus 100. This is going to be 200 ohms, okay? So that's nice. The next step here is we combine these in parallel. When combined in parallel, you have one resistance, okay? You got an IS and you've got REQ3. Because these are in parallel, 1 over REQ3 is equal to 1 over REQ1 plus 1 over REQ2. Okay, so this is equal to 1 over 200 plus 1 over 200. The end result is 1 over 100. So Req of 3 is equal to 100 ohms. What? That was unintentional. All right, so now that we have that, we step back into the system. We know the current, we know the voltage between 1 and 4. If we were writing out our node voltage table here for this part of the problem, we've got 1, 2, 3, 4, 5, A, B. We know 4 is at 0. We can now calculate what node voltage 1 is, okay? So VREQ 3 is equal to IREQ 3 times REQ 3. We know this value, we know this value. So we plug in 0.1, we multiply that by 100, and we get VREQ 3 is equal to 10 volts. Okay, so I'm going to go ahead and write that in right there. Now I also know that node 1 and 2 are already connected, which means I know a whole lot more voltage than I thought I did. Oh, I know, right? Whoa. Now, I'm going to step back 1, and I got the voltage between 1 and 4, and I am trying to figure out the current only in this loop, okay? So VREQ2 is equal to IREQ2 times REQ2. Here I know what REQ2 is, it's 200. IREQ2 I don't know. VREQ2 is equal to 10. So 10 is equal to IREQ2 times 200, which means IREQ2 is equal to 0.05 amps. We're done. We are actually done except for the part where we calculate our Thevenin. Because the amount of current that goes through this loop is the amount of current that goes through this loop. Now, this is all shorted. So all of the current that goes from 1 to 2 goes from A to B, which is great. Which means we know ISC. And I'm going to go ahead and write that over here. VOC is equal to 2.22. ISC is equal to 0.05 amps. Okay? So when we go to construct our Norton and Thevenin equivalent circuits, hello! You know, my parents never took me to the Children's Museum when I was a kid.
Children's Museum?
I don't want to. I play with the camera as much as I want now.
It's a children's museum.
It's like a place where you can have fun and play with cameras and like all the fun mirrors. My parents never took me to daycare when I was a kid either. My parents never took me to carnivals.
Really? You never went on like that little Scooby-Doo thing where you just walked through it?
He had a really fun corner that I sat in all day.
Did I have a nice wooden stool?
You must have had
No, we were too poor for the wooden stool.
You must have had a socket that you can paperclip in now.
No, I found that outside.
Oh.
I used to think there was a dragon. Okay, let's finish this. All right. So I'm just going to draw the Thevenin and Norton equivalent circuits. VT, RT, ISC, RT. Okay, and we know that RT is equal to VOC over ISC, which is equal to 10 divided by 0.05. No, thank you. It is not 10. 2.222 divided by 0.05.
So are these circuits always going to look like that? You don't have to try and like fit that inside of the original circuit?
Yeah. This is it. The idea is that we've replaced this entire circuit with this. So now, instead of, oh, I'm getting ahead of myself. Let me solve this real quick. So this is, yeah, RT is equal to 44.44 ohms, okay? So now we have this value, and then we have these two values, and we have solved the Thevenin and Norton equivalent circuits, okay? Now, why did we do this? The idea here is if I were to plug in a resistance between A and B on this circuit, and it was going to be a variable resistance, something that went from 0 to 10 kilo ohms, something like that, or 0 to 1,000 ohms, I can instead plug that same resistance into this circuit and solve it this way. This one's much simpler, okay? And the math on this is much simpler. Now, the irony of that is you had to do a ton of work to figure this out. Seth is just like, no, this is not simpler. Playing with your mask.
More than one value. Yeah.
Right, then it becomes simpler because then you don't have to solve the circuit every time. Now the flip end of that is we can also take a different approach to this, okay? One approach is if you're gonna try to solve this circuit and you want to do this experimentally rather than theoretically, experimentally means you actually measure it, theoretically means you solve the calculations. This is 10 million times easier, okay? Because what do? You take a really, really high value resistance, which by the way is included in a voltmeter. You just touch the voltmeter to A and B when it's open. Done. You now know what the open circuit voltage is. You didn't have to calculate anything. Second step, you then put the voltmeter as a current source, as a current meter, an ammeter. You put it between A and B, you then measure the current. Done. Short circuit current. You take two measurements, you solve for RT, you are done. So, moral of this story, experimental values, they're easier to work with. But the concept here is you build this circuit this way, you make those two measurements, and now you can do all of the calculations that you want here in a much easier format. All right? Okay, you have homework due tonight. You have 2 reading assignments. You have a quiz. You have a question.
Why did you change node 1 voltage from 11.111 to 10?
Oh, because in 11.111 was when this was an open circuit. When we went back and had to solve it again, I erased everything.
So they're 2 separate things?
They're 2 separate circuits. When we short this, you can't take the math from the previous one because when we shorted this, we had completely ignored 1 and 2, which we didn't do in the first circuit. That is a great question, though, and that is a question that everybody has every year. So it's good, very observant.